All right, I think we can start. Welcome everybody. So today I'm Tony, and this is Divya, and we're going to be talking about getting started with transformers for computer vision. So at the end of this, you should have a basic understanding of what transformers are, how they work, and then Divya is going to show you how to actually use it like in a Jupyter notebook. It actually is super easy now with Hugging Face. That's what we'll be talking about. So the latest decade basically has all been deep learning, driving kind of the AI, this latest wave of AI. Computer vision and natural language processing, NLP, have been kind of the two big areas of this. It can be argued that 2012 with AlexNet and Alex Krzyzewski's paper, that really started this latest resurgence of CNNs for computer vision. That was an image classification, but then object segmentation, semantic segmentation. The one Divya is going to show you is object segmentation, or well, actually object classification, object detection. So yeah, and then natural language processing. 2017 is really when the Vaswani Google Brain paper came out with "Attention is All You Need," talking about this transformer model. It was a brand new type of neural network, or I'll show you it's almost brand new. There's really just one change to things that we are used to, and that literally transformed the NLP community. This is really what people use now. So transformers, the big T, like ChatGPT. If you use any models with a T in it, it's probably a transformer model under the hood. What's so great about them, the whole reason that they were created was because initially for NLP, it was a lot of recurrent neural networks. Those were very hard to train on GPUs because there was the recurrence, the sequential part of it actually limited its ability to be parallelized. So the sequential part was hard for that task. Transformer models end up scaling. They don't have to be, there's no recurrence in it. You can actually scale it across lots of GPUs. And then there's the key takeaway was instead of recurrence, they had this attention module that I'll go through. But the idea here is this attention module, that was the thing that would learn relationships between words. And so in language, word position in the sentence is actually important in defining the meaning of that word. So this combination of parallelism with the attention mechanism, that really opened up the doorway to this. And so I talked about two different fields, CNNs being for computer vision and transformers being for NLP. Transformers actually can be used in computer vision as well. The idea here is this is an image is worth 16 by 16 words. They literally just take a picture and divide it into a 16 by 16 grid, and each tile of the image is a quote-unquote word, and now you can feed it in and pretend like an image is a language by just breaking an image apart into tiles and considering each word to be each tile to be a token of the language that you're dealing with. If you look up here with the transformer encoder, this is the basis of the network for the transformer. The norm layer and the MLP, the multi-layered perceptron, those were there before. It's really just this multi-head attention that is the new thing. And so that's what I want to describe, and then we'll go into an actual implementation. Okay, so it's harder to describe with the pictures being divided into tiles. It's a little bit easier to describe in the NLP domain because we have words and we all understand words. But the idea is there's some like atomic, structure. There's some like smallest part of the thing. A word or a word piece or a token is the smallest part of the thing. But something like the word park with these three sentences means slightly different things. And it depends on the other word. It depends on where it is in the sentence, and it depends on the other words that are in the sentence. And so this is what they were trying to solve with this attentional layer, is being able to change the meaning of the word park based off of the other words that were in the sentence. With everything in a computer, it's got to go into a number form at some point. So it knows nothing about it knows nothing about the word park, the letters P-A-R-K. It just needs to be put into a number form. And so if in fancy terms, we call this an embedding space, but just think about it as this room, right? If each person is a word in the language, so you're the word park, you're the word soccer, you're the word two, something like that. So everybody's a word in this space. If I just say I'm 0, 0, I can define in a two-dimensional grid like two numbers that define where you are in the space. And it turns out that you can train models to create this for all words in a language. And the way it usually end up being training is that words that are similar, so all the animals are back there and all the colors are in one cluster and all of the meals and food are in another cluster and all the transportation is in another cluster. So words that are similar in meaning seem to be in similar clusters in the language. And so they're going to play on that with this. So imagine if you had, this is the space. So I'm just showing it as 2 dimensions. It's actually 768 dimensions. I'm doing the BERT model here. This is the embedding space for this sentence. Initially in this room, the word park would have been here in this open circle here. The other words here, so your park, the words soccer and play are like over here. They're actually pulling on you and moving you slightly in the room, slightly within the embedding space. So now you're slightly offset to the original meaning of the word play into this new version of the word play. So they call this attention, like how much you're in your same space, but how hard you pull park. That's the thing that it's learning, is how hard it should pull. So if I'm doing this sentence, it pulls it this way. If I'm doing this sentence, well, now maybe there's another word, garage or something like that, that's out here. That's moving you in a slightly different place. And so for the 3 different sentences, park is about in the right place, but it's in slightly different places, and that gives it the different context, the different meanings. So that's how the attentional layer is working, is it's just saying that if we consider this room to be an embedding space, words are living there, words that are close together mean certain things. We can just perturb the space a little bit. We can morph the space a little bit, and that's what you see in these 3. I'm going to move it over because this is pretty complex, but Divya's going to show you how easy this actually is and how most of this has been done for you in Hugging Face.
Thank you, Tony. Hi. So basically, I'm going to talk about, if you are curious about transformers, how you can use them and how you can use them for image-based tasks. So the Hugging Face platform is a platform where a lot of pre-trained ML AI models are available, and you can just plug and play, essentially. The big success Hugging Face has had is with the Transformers library. And Hugging Face has a lot of different annotated data sets. So in my daily life, I work a lot with images. But if I am curious about any other type of data set, I can log in and I can, look at audio, video, text, and start playing with it. If you were just go to the landing page, you will see they have about 2 million models, 500,000 data sets, something called tasks and spaces. Tasks is basically the different machine learning tasks they have and the models they have to accomplish these tasks, which could be image, object segmentation, image classification, text-to-image generation, etc. And space is the part of the platform where you can deploy your code. If I do a search with the word transformer on Hugging Face, I end up with 1,000 models, 250 data sets. So yeah. Now, if I want to start with image classification, and so all you need to do is go to perhaps Google Colab, open up a notebook, or you can even set up an environment, open up a notebook locally, install the Transformers library, And here I took an image from the Hugging Face portal. This is an image of a bird, and it's essentially just 4 lines of code. And I get a classification result that this image is a macaw with a probability score of 1. So you basically from transformers will import this abstraction, which is called a pipeline. It is a user-friendly abstraction that allows you to use a pre-trained model on an image that you have just taken from the web. The main thing is you have to create this pipeline. I mean, here I can choose whatever name I want, a classifier, a pipe, put it in this abstraction. The first argument that goes in is the task you want to perform. In this case, I want to perform the classification task, and then I choose the model that will go in. So you have a lot of options on Hugging Face that you can pick for image classification. This happens to be the default model. So the main thing is specifying the task is mandatory. Specifying the model is optional. If you do not specify it, you will get the same result. So once you pipe your image through, you end up with a result. Result is a list of all the labels that have been generated, and the first element is the highest probability score, so most likely your classification. Now, if I wanted to segment these birds, all I need to do is change the task, object detection now. But because it's a different task, the model is different. The same rule applies, specifying the task is essential, model. If you do not specify, a default model will be pulled in. Same thing, the image is passed through this segment pipeline, and I have the result like it shows up in segmentation models. You have a probability score, you have a label, and you have the bounding box. So 2 birds were identified with a probability score of 1. So the main point here is that the barrier to entry for a classification and segmentation task for a general image is just, it's very low. This is essentially 4 lines of code and you're getting your result out. I am showing here, these are 4 different images from the COCO data set, and they have been passed again in this 4 lines of code, and it does a pretty good job. You have all your detections. So yeah, it's easy. But Tony and I live in the world of biological images. So what happens if we just take some of the images we are used to and put it through this pipeline? So these are examples of GFP tagged cells that I just picked from the internet, and clearly the model is failing. So that is the first result, or the first sort of thing I want to pass on here, that default models will definitely fail on custom image data sets. So depending on your problem, depending on your imaging data set, you will have to tune these models. So here's a case study. I wanted to look at breast cancer classification. So the first thing I did is I went to the Hugging Face portal and I looked for a data set for cancer images. I came across this multi-scale, multi-cancer data set. So this had about 130,000 images of several cancer types. So I took a subset of these images. So I identified all breast cancer images. So that was about 10,000 of those, 2 different categories, benign, malignant, and you push it to the hub. So this way, I generated a practice data set. So now this is available for anybody to use. If you want to play with breast cancer data classification, you can go and simply load this data set in the notebook, and you will have the it's again a transformers abstraction called dataset dictionary. So now I have 7,500 images in the train data set, 1250 in validation, and 1250 in test. So you can, this is an example of what those images look like. These are histopathology images, different from the GFP tagged images. But there is just in the biology space, there is a lot of variability within the kind of image data one comes across, the modality which is being used for imaging, the task you have on hand. So yeah, it can be very varied. If I were to take it and put it into my 4 simple lines and do an image classification task, this is what I get. Image was classified as a nematode, highest probability of 0.028. So no, it won't work. You have to. So what can you do? You have to fine tune a model. And the fine tuning part is that here I'm choosing to work with the Google Vision Transformer model. So I can just call it in. And the main thing is you freeze all the model layers, but train the final classification layer. And that also is achievable. So it's easy to familiarize yourself with the transformers library and use it. So again, in 3 lines of code, I have instructed the code that, okay, freeze all the layers, only train the classification layer. And then you run the training. This is my result. I trained the model only for 3 epochs in the interest of time. It took about 40 minutes, and on the validation data set, it gave me 96% accuracy. Recall, if you plot the confusion matrix, the recall is pretty bad, 48% recall for malignant cancers. So 2 lessons here. For breast cancer classification or cancer classification, accuracy should not be the metric, number 1. And one has to improve recall. Recall is the one that is important. The other thing I want to say, I did not show this model all of the 7,500 images. I actually only showed 1,000 images. So now I have run an exercise end to end, but I have to go back and now figure out how I can improve this performance. But overall, it's a nice little project to familiarize oneself with the Hugging Face platform and to work with Transformers library, and if you have never worked with image data, to get started with computer vision as well. So the point is, if you were to do this 10 years ago, you would be sitting and writing the model. But right now, things are different, and yeah, I will repeat myself, barrier to entry is low. What are the pain points? Just from experience, in any image-based problem, the pain point is always the annotated data set. Depending on what problem you are wanting to solve, you have to make sure the data is available. It always takes a lot of time, effort, and money to generate and annotate data, particularly biology-based data sets. The other thing I will say is it's important to get clarity on how the model is ingesting data. These are all tensor-based models, right? You need to be very sure what dimension is going in, what dimension is coming out. That's a slippery slope. Also, I only showed classification today. If you work with segmentation data sets, they are slightly more complicated to prepare them for training and for model ingestion. And in terms of training hardware, I did this on my laptop, so I quickly ran into issues. So if you're dealing with complex data, big data sets, you need to consider how you are going to get access to compute power. So the wins, though, it's easy to set up, it's easy to get started. You have a lot of different types of models, data sets, and tasks you can explore on Hugging Face. Really, curiosity is the limiting factor. And a lot of different resources are available. Hugging Face itself is a good resource. YouTube is a good resource. And I will do a little bit of self-promotion. I have all of the work that I have shown here, as well as some extra work, is in the form of these transformer tutorials on GitHub. So these are all notebooks that you can open in Colab and run, yeah, if you so choose. So I think that's the end of our talk. Thank you so much for your time.